Here's the other big way for preparing alcohols from carbonyl compounds. In the last slide we saw just direct reaction with H2, with hydrogen molecules. Hydrogen can be difficult to work with as a gas. It's hard to transfer without it escaping, and it's a flammable gas. So if we're just making small quantities of alcohols by reduction, these are some good alternatives here. Metal hydrides, for the most part, it's these two. These are the two we're going to focus on. Sodium borohydride, NaBH4, and next to that, lithium aluminum hydride. Both of those are white solids. They can be dissolved along with the corresponding carbonyl compound, and usually these reactions happen pretty quickly at room temperature and give good yields of product. Sodium borohydride, the first one's especially convenient because you can use it in water or alcohols, so you don't need any fancy solvents. And although sodium borohydride slowly does decompose by reacting with water and alcohols, if you do have an aldehyde present or a ketone present, it does give good yields in that instance. The hydrogens that end up turning the carbon into the CH2, those come from the hydrogen in the borohydride, and as it says right above that, these can be considered as a source of hydrogen with negative charge, hydrogen with 2 electrons. That's what hydride is. And the solvent ends up being the source of the OH hydrogen at the end. But we just want to be able to recognize that when NaBH4 is given as a reactant, it reduces aldehydes or ketones to the corresponding alcohol. So the molecule picks up a net gain of 2 hydrogens. The second one here, lithium aluminum hydride, as it says at the bottom, it's more reactive, it's stronger. It can be used in cases where the sodium borohydride doesn't react as quickly. And the only thing with lithium aluminum hydride is you can't use it in water because water decomposes it almost on contact. So you have to use something that's not water, that's not an alcohol. Ethers are molecules that can be considered as isomers of alcohols. Here's the most famous ether. This is called dimethyl ether. The oxygen there is not directly connected to a hydrogen, which makes it a lot less reactive towards lithium aluminum hydride than if it did have its own OH group. In any case, the net result for both of these reactions is the same product. You make the corresponding alcohol. And if you're starting with an aldehyde, it will make a primary alcohol. If you're starting with a secondary, if you're starting with a ketone, you'll make a secondary alcohol. Lithium aluminum hydride, again, requires kind of a special solvent. You can't use just plain old water. But it does have the advantage of being powerful enough to reduce carboxylic acid directly to the corresponding alcohol. So it takes out it takes out a net change of one of the oxygens from the acid, and we add a couple of hydrogens as well. So whatever else is going on with the acid, whatever the R group here is, the net effect is we just reduce this all the way down to the alcohol. And that's handy to be able to do that. As it says there, you can't use just plain H2. Hydrogenation will not work to do this kind of reduction, and lithium aluminum hydride really comes in handy because it is powerful enough to do that. By the way this is listed as a 1 and 2 means you can't add the lithium aluminum hydride in ether and the water all at once. You would react the acid with the lithium aluminum hydride, in which you take care to leave the water out, and then as a second step you then add water to give you the corresponding alcohol. So a very handy kind of reaction that goes pretty easily, especially in a fairly small scale like what we have in the laboratory. What's handy also about lithium aluminum hydride is that it tends to be specific for reducing carbon-oxygen bonds to the exclusion of carbon-carbon double bonds. Sometimes we may want to do our reaction at the carbon-carbon double bond. Sometimes we are trying to avoid that. So it's nice to have a choice. So you can see this big molecule here is part ketone, part alkene. And if you do the reduction reaction with lithium aluminum hydride, you can see the product is that we are reducing the carbonyl to the OH group while leaving the carbon-carbon double bond unchanged. And as it says at the bottom, if in fact we wanted to react the carbon-carbon double bond and do the reduction at that part of the molecule, H2 would be the better choice because it tends to prefer to react with the carbon-carbon double bond and leave the carbonyl alone, so that we would have a choice of which part of the molecule we are reducing, assuming that we did want to choose between one or the other. Anyway, that's kind of a quick lesson on doing reductions, and there are exercises and worksheets to kind of see this in context for you to practice on.